All right, so the last talk today is Henry Wilton. He'll talk to us about surface subgroups and graphs of free groups.
Thanks very much. It's been a real pleasure to be here. I've had a lovely time and a great conference. Maybe as the last speaker, it's just good to suggest, I think we should also thank you to the organisers for organising the fantastic.
Good job, Brian.
Let me see one of them. Right, okay, so today I'm going to be talking about hyperbolic group G. It's going to be non-virtually free. And hyperbolic, yeah. Okay. And we're going to address this famous question of Gromov that I probably don't really need to write down, but I will. Which is, if I've got such a hyperbolic group, must G contain a, let's say, quasi-convex surface subgroup? So I think there are plenty of interesting things to say about the motivation for that question, actually, but I'm not going to do that today. I think in this conference it's okay to assume that that's an interesting question. Surfaces are in the title. Okay, so what do I mean by, just to be really clear, what do I mean by a surface subgroup? I think I mean the same thing that Mia may have said in his talk. Anyway, so in other words, I want to have the fundamental group of sigma, where sigma is a two-manifold which is closed, and that fundamental group is supposed to embed into G. Oh, and I want the Euler characteristic of sigma to be non-positive. Okay? So a priori, sigma could be a torus, but of course in a hyperbolic group it won't be. So that's fine, right? But that makes one statement later on. Right. So there's been a lot of work on this topic, and I'm not going to exhaustively list every bit of work that's been done. It will take me all of my 50 minutes. But I will, of course, just mention a couple of the sort of highlights. Of course, you probably. So, of course, famously, Kahn and Markovich in about 2009 answered this question positively when G was the fundamental group of a three-manifold. I said a hyperbolic three-manifold, but it's already got to be a hyperbolic group, so that's good. Right, so that's. And then another fantastic bit of work was a theorem by Caligari and Walker in, I think it went on the archive in 2013. And they were able to answer the question positively when G is a random group. This is in Gromov's density model of density less than a half. So I don't think we've had the definition of random groups. Yeah, yes we have, or maybe we have. Oh, we have. Good, excellent. We have had the definition of groups. Great. So then you know exactly what I mean. Anyway, in particular, this is sort of, this is all the densities at which you get infinite hyperbolic groups. So, this was a really good. This was a, that theorem just sort of was as best possible. Right, and today, as the title suggests, we're going to look at a setting that looks rather, arguably is rather easier than either of these. So we're going to look at the situation where G can be written as, say, an amalgamated product. So I might write it as f star f prime over some h. Or maybe G could be written as an H and N extension. So f star for H. Or more generally, where it's a graph of groups. But it can actually reduce very quickly to these cases, so we don't need to worry too much about more general graphs of groups. But the key thing here is that we're going to want F prime and H all to be free and finitely generated. So those are the kinds of graphs of groups we're going to look at. Now, of course, that's, I like that situation because it's very concrete. Free groups, nice and concrete, fundamental groups of graphs, so we can get them in our hands. Much easier to think about, I think, than an arbitrary hyperbolic three-manifold or an arbitrary random group. But actually, there's a serious disadvantage to this setup, or a serious challenge in the setup, which is that, remember, G doesn't just have to be hyperbolic, it also has to be not virtually free. And we know that, because if you've got a virtually free group, you can't possibly have a surface. Okay? But if I give you a group that's written like this, or like this, it might be free, right? And it might be just hidden. It might be you can have really complicated graph of groups decompositions of free groups. Right? And so you might be given a group that on the face of it you thought wasn't free, but actually secretly turned out to be free, right? And so in that case, if you take one of those groups and you start looking for a surface subgroup, you're going to be looking for a very long time. Right? So at some point, there's a technical challenge in this setting, which is you do have to be able to recognize that you're looking at a non-free group. Whereas of course, actually for Karl Markovic and Kagaran, that issue doesn't arise. These groups are never free. Okay, so MB, G might a priori be free. Okay, so anything we do has to sort of think of it. Alright, so what I'm going to do is I'm going to try to give a sort of a roughly historical account of how work on these kind of settings has developed, and I'll try to, hopefully, and when I do that, I'll give you some idea of some of the tools that are used, and I can state some theorems, some of them old, some of them new. So the first thing I'm going to do is in this first section, I'm going to discuss an important tool, which is called Normalized Euler characteristic. And hopefully you'll quickly see that it's a good thing to think about. Okay. But, alright, so we're not there just yet. So suppose I've given you one of these graphs of groups, and we want to look for a surface. Okay. So what do we start by doing? We start by drawing a picture. Right. So suppose G has a surface. Well, what would the picture look like in that case? Okay. Well, my graph of groups, of course, I want to realize it if I want to picture what's going on, I should realize it as a graph of spaces, right? And because my vertex groups are free groups, they're going to be graphs, and I'm just going to have a graph of graphs. Right? That's what I'm going to look at. So it might look something like this. So I'll have a couple of graphs which I'll call gamma and gamma prime. So pi1 of this one will be f, and pi1 of this one will be prime. And then in the middle, I'll have some graph which for ease I'm going to draw as a circle, but it could in general be a more complicated graph, and I'll call delta, and pi1 of that delta will be h. Okay? And because h is realized as a subgroup of both f and f prime, I get maps from this middle graph into these other two graphs, and so I can use that to construct a graph of spaces by crossing delta with an interval and then gluing the ends to the graphs. Okay? Okay, so there's my graph of spaces. Now suppose it contains a surface subgroup. Okay? So that means there's some. That's because we're dealing with k pi 1s here. There'll be a nice map. I can realize that by a nice map of a surface. So maybe it looks something like this. Could be a pretty crazy surface, right? Right, so maybe there's a surface that looks like that and that maps down. My picture is almost too big for it, got a bit squashed, but hopefully you can see what's going on. All right. And so once you start drawing this picture, one of the first things you're led to do is you are led to make your map transverse to this middle delta, which you can, and then look at the pre-images here, and what you do is you can arrange for them all to be essential, simple closed curves. So, you end up in the picture that looks like that. Okay. And so, you stare at that picture for a while, and you end up realizing, I'm really delighted to be following Daniel's talk, because of course, what you end up realizing is that you really need to solve this kind of problem for graphs, what Daniel calls graphs with fins. Okay. So if I cut along this guy here, right, I'm going to have a graph with fins. Right? And the challenge is going to be to find an interesting surface with boundary that maps to the graph with fins. Now I don't call them graphs with fins, I call them something else. So I'm going to, the next thing I'm going to do is I'm going to give you the definition of the object that we're going to see.
Delta is more complicated than a circle, it's not quite a graph with things.
Yeah, sorry, you're right. Yes, that's true. That's true. But you're still going to need somewhere for the boundary components to go. So you'll end up with a similar. So let's just go with it. We'll see. Yeah. But we are going to be genuinely talking about those things. So we're led to study what I call graph pairs. Which will typically be something called gamma W. Right? And what that is it's just going to be a graph, a finite graph, and you might have a circle, S1, and W is going to be a nice map from the circle to the finite graph.
Okay. In general.
Or more generally, it might be a disjoint union of circles.
Delta actually has some.
That's true, but I'm not going to talk about that. Okay, we'll get there. Or more generally, disjoint unions. Yeah. Someone in Cambridge, in the Isaac Newton thing, last year, kept saying to people interrupting from the audience, "Patience, young Padawan." I can see that I'm going to have to adopt this. Yeah. So you're right, and then more generally, sooner or later we might want to think about analogous things where we have more complicated graphs. But for now, this is going to be. So yes, we're going to match from circles into gamma, or a circle, or more generally a disjoint union. So that's a graph pair, and hopefully you can see that it's almost identical to these graphs with fins that Daniel was studying. That's just the mapping process. Sorry, the mapping cylinder. So, right. So now, let me give you an example. There's an important example in these kinds of things. So, if sigma is a compact surface with boundary, then one thing we can do is we can take our graph gamma to be a spine for that surface. So we can take gamma to be a spine, and W to be a natural projection from the boundary of the surface onto the spine. Okay, so that's an example of the sort of thing that we of these graph pairs, and it's a special kind of example. It's a fat graph. Okay? So this is in this case, it's a fat graph. In this case, gamma W is a fat graph, and I will often just write it as sigma of boundary sigma, just because it's a convenient way to do it. Let me draw you a picture in case you're confused about what I mean by spine. Here's a good example of the sort of thing I'm talking about. Near the surface. So there's an example of a surface with boundary. Okay, fill that in. And now my graph gamma is going to be a spine, so it's going to just vertices are going to live there, and the edges are going to go between them like that. And then it's easy to see what the boundary is, this curve that goes around the outside, and it's easy to see how to project it onto this. Little exercise, you can work out which surface this is. That's it. Fine exercise. Alright. Okay, so hopefully we're all clear about graphs. Okay. Alright, and then we're going to need to sound a little bit like category theorists for a second, which I apologize. Definition. So a morphism of graph pairs is a commutative diagram, right? So suppose, okay, so my morphism of graph pairs, so it might be called F, and it wants to go from the graph pair lambda u to the graph pair gamma w. What should that look like? Well, I've got my graph lambda and my graph gamma, and I just want one to map to the other. But then I also have these circles, or disjoint unions of circles, u's mapping to lambda, and then disjoint union of circles mapping to gamma by w. And I want to have, not only do I want to map from lambda to gamma, but I also want a nice map between these circles, which I'll usually call df for the boundary. Right. So that's what a morphism is. And also, so there's also one extra condition which I'm just going to say, which is, so I want this df to actually be a covering map, which isn't so bad. It's just, and I actually want it to be a covering map of constant degree. So if you only have one circle here, that happens automatically. But if you have a number of circles, then you might have different degrees over different components, and I'm going to insist that the degree is always the same, as a well-defined. Okay? It's just something I'm going to insist. Alright, and so now I can finally define this useful tool, the normalized Euler characteristic. Which will hopefully look a bit familiar. So given one of these morphisms f, so the normalized Euler characteristic of f is a quantity that I'll call rho of f, and what it is it's minus the Euler characteristic of the graph lambda, okay, so the domain here, divided by the degree of this map df, which I've already insisted has to be well-defined. So this should look kind of familiar to you from, I think, from King's talk about SCL. So there are quantities, there's a quantity very like this that appears when you try to do things with SCL. Okay. So now what I'm going to do is I'm going to try to describe some theorems that go back. The first of them was proved probably 10 years ago, and they go back. But all of them, almost all of them, have something to do with this quantity. So we're going to use this quantity as like, every time we talk about a theorem, we can say how this quantity played a role. Hopefully you can find that. Okay. Any questions before we move on to the next step? Okay.
So the Euler characteristic of gamma
does not play a role in this definition. Gamma will usually be fixed, right? Gamma will usually be some fixed target.
And is degree algebraic or?
Sorry?
Is this degree function algebraic or just geometric function?
By which you mean is it oriented? Does it count with sign or not?
Right.
The answer is that I don't want to tell you. So sometimes it's convenient for it to be oriented, and sometimes, like in this generality, it can't be oriented, right? Because there's no real notion of orientation. Right? But there are situations where, in the situation where lambda happens to be, where the pair lambda is actually a fact graph, you could make this. You can talk about you can talk about orientation on the boundary, and then you can count this degree with sign, and you get a slightly different quantity. And sometimes that's a really useful quantity to use. And the difference between those two things can be a major technical headache, and I'm not going to talk about it again now, because don't.
So if you have two circles mapping equal one, and one wraps around one way, and the other one wraps around the other way.
Right. That doesn't. That doesn't
mean anything.
They don't cancel each other.
Okay.
They don't count. They don't cancel.
Is the restriction on the degrees being the same, is that an opposite rule, or is it an essential restriction?
Well, if I don't do it, then I don't know how to talk about this number. That's.
You're going to get complexes out then.
Yeah.
Those might have some if you allow your degrees.
Yeah, right. There's nothing, on the face of it that's going to stop that. But I don't know how to talk about it. Any strategy of proof that involves this quantity, it seems to me that. Okay. All right. So, now we're going to so remember, G was a hyperbolic group. It's going to be some kind of graph of groups. So for section 2, it's going to be an amalgamated product over Z, right? Or more generally, it might also be an H and N extension. But we're just going to deal with over Z. So that's what we're going to address in section 2. And the first theorem that I want to state here is a theorem that Caligari proved in 2008. And what he proved was that for this kind of G, if H2 of G is non-zero, so if there's some second homology, then G has a surface set. Very nice theorem. Right. And so the thing about this theorem is he proved it using an even nicer theorem. Right? So that's the next thing I'll state. So it followed from theorem 2, which he also proved in 2008. Well, 2008 was a really good year for Danny. And that theorem said that stable commutator length, which is thankfully Jing defined, so I'm not going to define it again, is rational in free groups. So it's a rational, so the stable commutator length of an element of the free group is a, we'll have to do the commutator subgroup is a rational number. So, what I told you was that I would try to tell you what the theorems that I state have to do with this quantity graph. So let me try to say something like that. So, so first of all, I'll just try to tell you how theorem 1, I'll just give you a hint as to how theorem 1 follows from theorem, or can be deduced from theorem 2. Because it's cute, and it sort of gives an idea of why rho is a good thing for getting topological information. So 2 implies 1. Hint. That's the hint. So, oh, no, sorry. I just decided to do things in the wrong order, and I just realized if I do it in that order, you won't know what I'm talking about. So I have to do it the other way. Okay, right. First of all, let me give you a hint as to how to prove theorem 1. And you'll see, sorry, theorem 2. And you will see where this quantity rho plays a role. So, the idea of proof of theorem 2. Okay. So, consider the set which consists of all fat graphs, right, and allow them to map to just mapping to the pair gamma w. Okay, where w is just some fixed word. in your free group. Okay. You should probably think of it actually as being, sorry, so maybe best to think of it as being in the commutator subgroup. Then it will have a stable commutator. Okay. So you can just look at the set. And on the face of it, you might think that this was a completely insanely large set, but actually the amazing thing is that this set has the structure of a sort of linear cone.
Is gamma just some rows realizing?
Gamma is still a graph whose fundamental group is F. Okay? I was thinking that sort of to say why this is some sort of linear cone was going to be something that I would just have to brush under the carpet, but instead I'm going to refer you to what Daniel said in his last talk, because it's exactly the same. Okay? So Daniel was using some pieces of graph that you can glue together subject to certain linear constraints. And that's exactly the reason why this set is actually a reasonable set. It's like a sort of linear structure. Okay. And then what you do is you consider how rho, this quantity that I was talking about before, behaves on this set. And it turns out you can turn this into a linear programming problem. And the conclusion is.
So since you're saying it's a linear structure, so fat graphs are possibly disconnected and W is possibly a union of
well, yeah, W could, yeah, that's fine. Yeah. Or a union of elements that collectively form a boundary. Yeah, that's right. But certainly, yeah, I mean, fat graphs can definitely disconnect. It's really important. I very rarely want to assume connectivity. So we consider how rho behaves on a set, and by phrasing it as a linear programming problem, what Danny was able to show is that rho contains a minimum on some, what he called an extremal fat graph, sigma, boundary sigma, mapping to. Okay. And the point is that this minimum, what was this minimum? Well, when you stare at it for a while, you realize that this is precisely the stable commutator length of the work done. So that's the way that proof works, and you can see that rho plays a crucial role. So rho's that way. It's very close to related. So I thought I don't think I've got time to, as an exercise, it is a fun exercise to try to figure out how you get theorem 1 from theorem 2, but I think actually I don't have time. Let me just, the exercise, which sort of gives you a hint, is to prove, if you can do the exercise, it's fun and not terribly difficult, is to show that extremal surfaces are pi1 injective. Okay. So on the face of it, this is just some extremal fat graphs. So on the face of it, this is just some map of graphs. There's no particular reason for it to be pi1 injective. But actually, it turns out that the fact that it was extremal, in other words, that it minimizes rho, is enough to guarantee. And again, you can think about Thurston law in that regard. If you like this. So that's theorem 1 and theorem 2. Okay, so another important bit of sort of prehistory for this result. For the things that we're talking about today are what I'll call theorem 3, and that's the theorem that I proved in 2010. Remember, we're still talking about groups G that are graphs of free groups with cyclic intervals. And the theorem says that either G is pi1 of a surface, right? So that's one possibility. Those are graphs of free groups with cyclic groups. Just cut the surface somewhere along a simple post curve. You wrote it as a graph of free groups. Okay. Or G G has a non-free subgroup of infinite index. And so I don't want to. I'm not going to tell you how the proof of that result goes, but hopefully you can see it's sort of evidence towards the idea that these guys should have surface subgroups, because if they're not themselves surfaces, then there should be some deeper subgroup that has a chance of having a surface subgroup. But tools, I think something that is quite interesting is just to sort of be aware of what was used in the proof of this, because they continue to be important. So, so one important tool was Whitehead theory, which is, that's how you recognize whether or not this graph of groups is actually secretly a free. You do it by recognizing whether or not the cyclic subgroup you're looking at is secretly a free factor. Okay? And that's what Whitehead explained how to do that a long time ago, but I was particularly influenced by a version that Jason first described, I think. And there's also some work by Cashin and Makura, which was also mentioned by Daniel last time, but in the last talk, which was also sort of important. And another important tool in the proof was JSJ theory. Okay. And then finally, and the last tool, which I also want to mention, is, because it's very relevant to this conference, is clean covers. Which is a sort of, if you don't know about that, it's something that Dani introduced a long time ago, and it was really the first version of this special cube complexes. It was like how special cube complexes work out in the simplest possible case. So this was, and that turned out to play a crucial role in this thing, and sort of somehow has ramifications all the way through this. So there's a whole bunch of different tools there, and as I said, some of them things that we've been talking about a lot. Good. All right. Okay, and so after putting all these pieces together, so a few years down the line, we see this theorem that many of you have seen me talk about before, so I'll try not to say too much more about it today, but it just resolves the problem in this case, and that was, I guess, 2017, which was that in fact these sorts of G do have surface subgroups. In other words, graphs of free groups with cyclic edge groups. If they're hyperbolic and not themselves free, then they have a surface subgroup. Oh, and it is a quasi-convex one, as well, in case you want that. And somehow the proof of theorem A uses both theorem 1 and theorem 1/2 and theorem 3, so it's some sort of combination of all these things. But there's one additional important idea, which was somehow what was missing when those bits were working out, which was
Terribly tired of that. I've spread it over G as opposed to that surface subgroup.
I did, you're right. Yeah. Well, looks like there you go. Then you might.
Is G has the hypotheses there?
G has the standing hypotheses that I'm trying to build up. But there's an additional key idea which I want to mention, which somehow telling all these other things was supposed to sort of was supposed to soften you up and make you ready. So let's call a graph pair lambda u irreducible if pi1 of lambda doesn't split freely relative to u, relative to these cycles that we've given. In other words, these conjugacy classes of elements. So this is exactly like the rigidity hypothesis that Daniel made in his talk, except that I'm only concerned about free splittings, not cyclic splittings. Right? So that's the only thing we can compare. And then, so we're going to look at morphisms f from lambda u to gamma w, where we're going to assume that these lambda u pairs are irreducible. And the key idea is that if rho of f is maximal, so it's not like in SPSCL in the rationality theorem where you're trying to make it minimal, it's the opposite, you're trying to make it maximal. If you make rho of f maximal, then it turns out that this implies, slight line warning but not very much, that lambda u is a fat graph. So that's where the surfaces come from. They come from maximizing rho. That's what reduces them out of nothing, which is sort of where they come. Yes, that's where they come. So hopefully, maybe that's the key idea that you should take away from or take away more. So any questions about that? Okay, so I think I've got 15 minutes left. I'm going to, that's all stuff. You've either, I mean, some of it's relatively old, some of it's stuff you may have seen me talk about before. I'm going to try to talk about some new stuff in my last 15 minutes.
Sorry, how many surface groups can you get from this?
How many?
Yes.
Well, I can pass to finite index subgroups of any one I find and get an infinite family. So, I mean, but that's not a terribly interesting answer. I mean, it's not clear to me that like the ubiquity that Neil was talking about is meaningful. These groups are rather small. They've got the boundary is just basically all local couplings. So, sort of trying to separate that with a circle doesn't seem like a terribly sensible thing to do. I don't know. I'm not sure. Maybe it's difficult to stop.
It's still plane.
Sorry? Yeah, it's often plane. Actually, the plane situation is easy because then it's a manifold. So then, anyway, all right. So, okay. Let's move on to part 3.
But I just ask you to say a sentence. So before, when you were trying to maximize things, you were doing it over this sort of linear set factor.
Yep.
But now you want to maximize over all morphisms.
All morphisms from irreducible things, but it's still linear. So I mean, it's linear because you can count. It's made out of gluing together finite many pieces, and you're just counting how many pieces.
Okay.
So is there a mini-max process going on? Right, first you maximize over things and get a factor out, and then you minimize over factors.
Looks that way, doesn't it? Okay, right. So section 3, as I say, new stuff. We're going to talk about amalgamating products, or indeed it could be H and N extensions, where the rank of H is bigger than or equal to 2. Okay, so in other words, the remaining things. And so, let me just remind you of a crucial definition. We say that H inside F, actually H is, I'll think of it in G. So G is, H and G is malnormal if it's as far from being normal as possible. In other words, if I conjugate H by G, I take the intersection with H, if I happen to get something that's non-trivial, then that can only happen if G is in H. Okay, so that's a well-known, standard, important definition. And so the theorem is that if H G is malnormal, this is for G of this form, okay, then G is either free or has a surface sub. Alright, so that's, so we can do all the malnormal graphs of free groups. So if your favorite sorts of graphs of free groups are H and N extensions, like 3 by cyclic groups or that sort of thing, don't worry, we'll come to them in a little bit, but they're not covered by this, but more like it, not on the face of it covered by this. Okay.
What's the convention with this H equal to G allowed?
Well, in that case, G will be free. So the theorem is certainly true.
No, you can have the H and N extension.
Oh because it's not malnormal.
Oh, H and N.
I mean, it wouldn't be equal to G. It would be equal to F, but it certainly wouldn't be malnormal.
Do you still require G to be hyperbolic?
Sorry? It will be hyperbolic under those circumstances. Okay, so let me try to. I can't tell you the whole proof, but I can tell you a useful tool that's going to arise. So remember, we've got our graph gamma, and as Saul was objecting earlier, for general graphs of groups, we're going to need to consider this graph delta, mapping into it. And now let's what we'll do is we're going to fix a graph pair with this guy as the domain, right? So we're going to fix some cycles in this guy. So I'm going to fix W mapping some cycles into delta, which then of course maps onto gamma. So this seems to be the right setup to think about. Now what we want to do is we want to study things of the following form. So we're going to have, maybe I'll draw a picture. So I've got my, here's gamma, and then I have some possibly more interesting graph delta mapping to it. And then I have some cycles mapping to that. And of course I want to try to study surfaces in this guy. So what I do is I'm going to think about surfaces that map to gamma and whose boundaries are going to map to W. And I'm going to want to think about subsurfaces that lift to delta. So subsurfaces that land inside this distinguished place. So in other words, I want to think about pictures like this. So the whole surface might look like this. So here's my surface sigma, and over here, here's the boundary of sigma. But I want to have a distinguished subsurface lambda. I want to have a distinguished subsurface lambda, which has the property that while I map sigma to gamma, I can lambda can all be pushed into delta. So lambda can all be pushed into this, can all be lifted to the map. Another way to say it would be, if I threw away the rest of sigma, then lambda would factor through the map from gamma would factor through it. And I want lambda to contain all the boundary. Okay, so the boundary of sigma is going to be a subset of the boundary. Okay. So we're going to study. We're going to study triples, well, morphisms of triples. So we're going to be mapping sigma, lambda, boundary of sigma to gamma, delta. Okay. So those are the sorts of objects we want to study. And the crucial quantity seems to be, so we're going to define a version of this rho now, so let's call this map F. Rho of F is going to be, so it's now a relative version of rho. And what we're going to have is we're going to have the Euler characteristic of lambda minus the Euler characteristic of sigma divided by the degree of the map on the boundary. And that seems to be the crucial, as you can see, it's a natural generalization of what we've been talking about so far. This seems to be crucial quantity. And since I'm running out of time, I'm just going to say it. But the point is that you can set everything up as one would for Corollaries theorem and prove that there's a minimal such thing if you can find a surface at all. And that minimal thing will satisfy, just like this exercise I asked you to do earlier, so that extreme will fat graphs have time injected. This minimal guy will have an incompressibility property, which means that basically, you can't push any more of sigma into lambda than you already have. You can't push any more of sigma into delta than you already have. So it's sort of incompressible at that. The complementary region to lambda is kind of incompressible. That's the sort of special.
You can't steal from sigma and give it to them.
That's right. That's it. That's exactly it. So Yeah, so anyway, so that's like the key tool in the proof of Gromov. Right, about 5 minutes left, is that correct? Yeah, so I will try to, I won't say any more about that. I will try to list some consequences, because I think some of them should be interesting. So, consequences. Okay, so there's a nice theorem which is really due to Gittig, MJ Rips, Sigiv, that's part of it, and then also another part of it should be due to Agnew and Wise. And when you put together their work, what you can deduce is that if G is hyperbolic and virtually special, then some finite index subgroup, G0 of G, has a quasi-convex malnormal hierarchy. Okay. So, what do I mean by that? I'll just say it in words because I'm running out of time. It just means you can pass to a finite index subgroup, and now you can split this guy as a graph of groups where the edge groups are malnormal, and you can keep on going and keep on going and keep on going with that procedure until you eventually get down to free groups. So something that you get out of this, a corollary of this, is that if your hyperbolic virtually special group wasn't free, if you look at this hierarchy and you go down to the second to last level, in other words, just before you hit free groups, you're going to have a malnormal graph of free groups. Well, yeah, you'll have a graph of free groups with malnormal elements. And so what we deduce from this is that every non-free hyperbolic virtually special group has one of these guys as a quasi-convex subgroup. So when you put all these together, you get as a corollary C is that all hyperbolic virtually special groups have surface. So you can answer Gromov's question in the virtually special case, which Agol tells us is just the cubic case. So that's all right. Okay. Surface what? And they are quasi-convex as well. All right. So there we are. In fact, if you don't care about hyperbolic groups, that's fine. So in fact, there's a nice theorem of Capras and Agrund, who said that virtually special groups that aren't hyperbolic have to have a quasi-convex z squared. Right? So in fact, I didn't say non-free. So this is supposed to have non-free. Anyway, right. Right, so Capras and Agrund tell me that if I'm not hyperbolic, I've actually got a quasi-convex z squared. And since I said at the beginning that I wanted to count z squared as a surface subgroup, which is good for lots of applications, you can use the Capras and Agrund theorem if you want to get rid of that hypothesis, and you can just say it holds for all virtually special groups. All right, so yeah, I mean, I'm pretty much out of time. You can list. We know a lot of hyperbolic virtually special groups. You can get surface subgroups for them this way. Quite a few of them are new. I think C'1 cyclic groups and 3 bicyclic groups. So they're known to be virtually special. So although they're not covered by this theorem, 3 bicyclic groups still do get surface subgroups as a result of this. Of course, another really great class of cubulated hyperbolic groups is hyperbolic through manifold groups. great to have an E proof of that. Unfortunately, you cubulate them by finding surface subgroups in them. So you should never, ever, ever use this result to try to claim that that gives a proof that there are certain surface subgroups in hyperbolic three-manifold groups. Okay, I'll stop. Any questions?
Do you think you could sort of drop the malnormal condition here and make it something weaker and still get positive results out
I
of it?
think, yeah, you might be able to. But you don't, I mean, because of the virtually special machinery, you don't need to do that. So I haven't thought hard about that. Because you can, if you just have finite width, for example, you can just turn that into malnormals by passing to a But yeah, I'm not sure that you need the full strength of that.
But I mean, if you wanted to try non-hyperbolic examples.
Yeah, oh, I see what you mean. Yeah, in principle, the machinery applies in non-hyperbolic situations. I certainly wouldn't expect it to find you. One reason why I want to count z squared is because if you did try to run it in those situations, I definitely would expect it to find you z squared. So I don't think you would expect it to be good at finding more complicated surfaces in this situation.
I think the question was asked earlier about, how many. So
Right.
maybe I could ask that question again, where like how fixed units, let's count them, or
Yeah, I don't know how to do anything like that with them, but I mean, yeah, at this point I don't know. I haven't had a chance to think about that's what I mean. I mean, there's somehow, I think this is very different from the Karl Marx picture. I mean, they sort of managed to show that there are surfaces all over the place. In these kinds of examples, so I mean, their techniques don't actually apply to these kinds of examples. And the reason is sort of, I think the reason is that you sort of have to find the surfaces where they're living rather than force them to be everywhere. I just don't think that's what's going on. That's my thought. But I mean, that's just a sort of gut feeling.
Any more questions? All right, let's thank Henry again.